Progress.
Yeah.
Give me one moment here. I'm just taking a roll. We're getting the majority of the roll down here. All right. Can you hear and see me? Okay, I'm seeing some nods. One second. First, are there any questions or concerns?
You don't want us to turn in the study guide, right?
No, don't turn in the study guide. Use it, excuse me, use it as a sheet for which you can focus what you're learning. Other questions? Okay. The goal today is to finish chapter 1. So come next Monday night at midnight, your chapter 1 quiz will be due. Your chapter 1 practice will be due. Getting it done at least one time. Remember, you can do it repeatedly. And your chapter 1 smart book assignment will be due. And if you look on the D2L site, right on this side over here, it gives you the due dates for when things are due on McGraw-Hill. Some of these haven't opened up yet. For example, I think this, I'm trying to think when the smart book for chapter 2 opens. It may have already opened, but it's going to open either right after class or during class.
I think it already opened because I just finished the chapter 1 practice,
Uh-huh.
and it was telling me that I had 2 assignments.
Okay.
Completed the one, so
Okay.
Okay, it says that the quiz is due the 20th and then the smart book is due the 22nd. Does that mean everything's due the 22nd or the 20th?
Bear with me just for a second here. My cat's sitting on my phone. He's here keeping me company. Where, buddy, I need my phone. I know. I wouldn't let him sit on my keyboard, so he's sleeping next to my laptop here. Give me a second here. Hey, and I see that you're here. Is there a problem? I just saw your email. Hey, and are you here?
Yes. Hold on.
So what, you want to tell me really quickly what the problem is?
I don't have a problem anymore. It was
worked? Okay,
yeah,
good. All right, good. Okay, I'm glad. So let me, bear with me just for a second here. I think I'm gonna make this, these should both be due on the 22nd. And I'm sorry, I messed up the dates on that. These should both be due on the 22nd. And I'll change that right after class. Or sometime right after class. The chapter 2 practice will be due at that same time. So all the 3 of these will be due at the same time. Why do I have 2 of those? Oh, come on. Bear with me just for a second here. I'll bet you I know what the problem is. Okay. So you don't have to, it looks like when I'm looking at your content, it looks like we have 2 smart book chapter 2s. You only have 1. Other questions? So know that I'm going to change this deadline to the 22nd Other questions? I think, were we right in this area? Or were we a little further along?
We stopped right at that body systems diagram.
So a little further.
Yeah.
All right, about right here.
Keep going.
Right here.
Keep going. Body systems right there. Yep.
Okay. So what this hierarchy of complexity, we often use what are called functions, concepts, maps to describe physiology, because the body is a hierarchy of complexity where the bottom levels will interact to form the upper levels. The bottom levels, like the atoms and the molecules, also dictate what reactions and what interactions and what levels will occur next. So the atoms and the molecules are going to dictate what structures form next and what interactions are going to occur. Anatomical variation. No two humans are exactly alike. Anatomy books show the most common organization of structures. However, some individuals lack certain muscles. Other individuals may have an atypical or variation in the number of vertebrae. Some individuals have a varying number of certain organs, for example, kidneys. Some people are born with one kidney. This summer, I started dabbling with the subject of forensics anthropology. So specifically looking at the skeleton and a little bit about the fingernails and so forth. But one thing that I learned that I never really considered before was development of the skeleton. And I learned, let me try to show this to you. I learned about something really weird that I never thought about. If you think about your scapula, your shoulder blade looks kind of like this. It's kind of like that. With your acromion process up here, remember the top part of your shoulder. And then you have a spine that kind of goes like this. Well, I learned as I've been studying this, dabbling into this forensics anthropology, and part of forensics anthropology is knowing how the skeleton develops. I learned that the scapula actually starts as about 7 different parts, and it fuses together between the age of 0 and 20. And so anyone below the age of 20 probably doesn't have a scapula that's intact like this, what you see on a skeleton. They are, because their scapula is still in the process of fusing into this complete whole. For example, this acromion process, this little top part that articulates with your clavicle up here, that acromion on some people will actually never fuse to the scapula. It's one part that it may or may never fuse, depending on whether that person was really big into archery or not, where you're constantly putting pressure right here to hold your bow. I'm not an archer person, but you're holding your bow because you're constantly putting pressure right there. That acromion process may never fuse to the scapula. And so it may actually look like when you see a skeleton with that, it may be that the acromion process will end up looking like a separate bone from the rest of the scapula because it will never fuse to the scapula. So that's an example of where we all show some anatomical variation. And things are constantly changing and constantly shifting. Yeah, I thought it was really, I thought, you know, for someone like me who feels like I know the skeleton fairly well, what I think I know as a skeleton is what most mature and adult skeletons look like after the age of like 40. But before that, it may not look like what I think the skeleton looks like. Bear with me just a second. I know I got some new people since I took roll at the very beginning, so I'm just writing down the name. Also, some individuals may have what's called situs inversus, which means that they have a left-right reversal of organ placement. For example, their heart is on the right side and not on the left side of their chest. Their stomach, it may not be on the left side, it may be more on the right side or towards the center. Normal variation or abnormal or anatomical variation. Normal kidney formation or normal position of your kidneys, and one on your left side, one on your right side, one on your left side. However, in some people, you may have, rather than having them almost on the same plane, you'll learn later that the left kidney is actually shifted downward a little bit by the liver. But normally they're closely on the same plane. In some people, you may find that the kidneys down, one of the kidneys is down in the pelvis. Or they may have a horseshoe-shaped kidney where the 2 kidneys are attached. Also, the branches coming off the aorta may vary. In normal in most people that we know, see, we have the brachiocephalic artery, the left common carotid artery, and the left subclavian artery. Well, what if the brachiocephalic artery and the left common carotid artery come off a common trunk rather than two separate vessels coming off the aorta? Or what if the left common carotid artery and the left subclavian come off one trunk? Any questions about this? There are basic life functions that distinguish living from non-living. That didn't work. Basic life functions that distinguish living from non-living. The first one is that we show on this hierarchy of complexity organization. We have organized pathways, organized systems. We have cellular composition. Remember that the smallest unit of life, structural unit of life, is a cell. So all of our organizations are composed of cells. We have metabolism. So we have the consistent and constant breakdown and buildup of molecules, and release of energy from the breakdown that can be used for the buildup of molecules. We're responsive. If you've ever curled your hair and grabbed the wrong end of a curling iron, we're pretty responsive. We'll talk about more why that matters so much as we go forward with this semester. We also can be responsive in that we move, or we can transport things from one area to another. We also show what's called homeostasis, which we'll talk about more in a couple slides here. Homeostasis is a big deal. It is the underlying theme for anatomy and physiology. It is what we talk about when we keeping things within physically tolerant limits and keeping things within certain narrow limits. So we'll go into more detail here in a second. We also, as living things develop, we can undergo cell differentiation and cell growth and reproduction. Cells divide, they can reproduce. We as living things can also evolve. If any of you have children, your children are not exactly 50% you and 50% of the other parent. There's not one chromosome, there's one chromosome coming from the mom, one chromosome coming from the dad, but that one chromosome that came from you is actually an intermix of the 2 chromosomes you got from your parents. So your children are not exactly 50% you and 50% their father. They evolve. That's why no person is ever exactly alike. So life is not a single property, but a collection of properties. Bear with me just for a second here. So cells are bear with me, I'm so sorry. Give me one moment. So cells are able to transport materials from one region of the cell to another, just as the body is able to transport substances to different locations, or skeletal muscles can transport you from the sofa to the refrigerator. What basic life process is illustrated by this description?
Movement.
Movement, correct. Homeostasis and feedback. Here's your definition of homeostasis. Homeostasis is the ability to detect change, activate mechanisms that oppose it, and thereby maintain relatively stable internal conditions within narrow limits. So the ability to detect a change. Just for a second here, I apologize. Ability to detect a change. Activate mechanisms that oppose it and bring things back to relatively stable internal conditions. A good example of this is your body temp. Your normal body temp about 97 point, no, wait, bear with me, 98.6. If you shift more than 2 degrees one way or the other, you're either, you are completely outside of homeostasis boundaries. So for example, you get down to 97.3. At that point, you're not doing very well. And your body is going to try to move you back towards 98.6. If you get up to 99.7, now you're looking at possibly having a fever. So we have very narrow limits within when our body can function and when it can't. Remember how structure and function are all related, and structure dictates function. So when the structure changes, the function changes. Temperature is going to alter structure. And if you alter structure, you alter function. So for example, room temperature falls to 19 degrees Celsius or 67 degrees Fahrenheit. A receptor such as your thermostat activates the furnace. The furnace puts out some heat. The heat brings the room temperature up to 20 degrees Celsius or 68 degrees Fahrenheit. And then the furnace shuts down. And the room cools down again to 19 degrees Celsius, and the thermostat is activated again. So we're constantly disrupting our system so we fall outside of the very narrow limits we have. It's consistent, and we're constantly having to bring it back. That's homeostasis. Is this ability to detect change, activate mechanisms that oppose it, and thereby maintain relatively stable internal conditions. Because of these feedback mechanisms that alter the original changes that triggered them, they're called feedback loops. For example, someone has a child. I know some of you, I'm sure you have children, some of you. And I don't have any children, but I definitely have cats. I have 3 cats. And my one cat, they're constantly getting into doing something they're not supposed to. And this morning when I first started my first class, my one cat started to get into some plants that he knows he's not supposed to be in. And so I go, Evan, and he immediately jumps out of the plants. That's called a negative feedback. So for example, I'm trying to think, let's say Alex has a child, and that child starts to go towards a hot stove, and Alex is like, Tommy, and Tommy moves away from the stove. That's a negative feedback. Positive feedback, catching your kids doing something right and encouraging them to keep going that direction. So we're going to have negative feedback loops and positive feedback loops. Homeostasis is specifically looking at pushing things back towards the narrow limits. We'll talk about how positive feedback loop is pushing them further out of homeostasis until their original stimulus is gone. What is the definition of homeostasis?
D.
Say it again. D is in delta?
Yes.
Yes, you're right. So the ability to maintain relatively stable internal conditions, even though the outside world is changing continuously. Components involved in feedback loops. stimulus causes a change in a variable that puts us in a state of homeostasis imbalance. That change is detected by a receptor. The receptor sends a signal along an afferent pathway. Afferent means, think of that as being an incoming signal. Afferent. Afferent pathway. Remember this word afferent always means incoming. So a signal coming in to the control center. Control center oftentimes is the nervous system. It can be other control centers though. There are other control centers besides the nervous system. Controls, so afferent signal comes in along the afferent pathway. Control center decides what it's going to do with that information and sends a signal along an efferent pathway. Think of efferent as meaning an exiting pathway or an outgoing pathway. So afferent, incoming, efferent, outgoing. Efferent pathway goes out to an effector. Effector does something to push that variable back into homeostasis. I think the two questions you have on your study guide, your one set asks you about the three components of a feedback loop, or three parts of a feedback loop. The receptor that senses a change, the control center that decides what to do with that change, and the effector that performs the change to bring things back. The other question is a negative feedback loop and the components of a negative feedback loop. Stimulus is the first one. Stimulus produces a change in a variable, causes a homeostatic imbalance. That change is detected by the second part, which is the receptor. The receptor sends that signal to the third part, which is the control center. The control center sends out an action or message for an action via the efferent pathway to the fourth part, which is the effector, which is going to perform the response that pushes that variable back into homeostasis. That's the negative feedback loop. Any questions first? For example, for maintaining homeostasis, temperature goes up, core body temperature goes up. Start to sweat, we get up to 99.5, start to sweat as a response to bring the temperature back down. Also, the blood vessels start to dilate at the surface of the skin to release some heat onto the surface that can then be cooled down by the sweat. After a certain time of this vasodilation and sweating, temperature drops down below the boundary, the other boundary. So boundary right here, other boundary right here. Things need to be kept within these limits. That's homeostasis. But they're constantly shifting between those two boundaries. So vasoconstriction, vessels get cold, get vasoconstriction of the blood vessels near the surface to retain heat to the body core. And shivering, we get our erector pili muscles that are attached to hairs on our arms to form goosebumps and start muscle contractions to generate heat, to bring the temperature back up. Another example of another negative feedback loop. Remember, negative feedback loops is things move slightly out of the boundaries, and a response as that change is sensed by a receptor. It sends that signal to a control center. Control center sends out a message to an effector saying, this is what I want you to do to bring things back. So wake up in the morning, person rises from the bed, they stand up, and all of a sudden their blood drains from their upper body into their lower feet because of gravity, creating an imbalance in the body where blood pressure has dropped below where it should be in the upper body. Baroreceptors, bear with me here. I'm going to introduce two words. Oh, yeah. So I'm going to introduce a few words here. Baro. Have you heard of a barometer before? Have you ever watched the Weather Channel and what is a barometer? Caitlin, what's a barometer? You're the only one that I can see here. So what's a barometer?
Doesn't have to do with like the temperature. Like
It has
that's
to, close. It has to do with the pressure. So a baroreceptor, what would a baroreceptor sense?
pressure.
Yep. So it's a receptor that senses pressure. We also have what are called thermoreceptors. So
Wouldn't
that
that be
sense,
temperature.
yep,
heat?
exactly. What other term was I going to explain here? Oh, one other term, at least for this example of negative feedback, is an integrating center is the same bear with me just for a second here. I'm sorry, new laptop to me. I'm still figuring it out sometimes. Bear with me. Where's your equals sign on your keyboard?
By the backspace. It should say plus and equal, and you have to hit shift.
You know what? I thought that was it, and I kept looking at it, and it didn't look right. Okay, control center. So baroreceptor, thermoreceptor, integrating center means it is the same thing or synonymous in this case with the control center. So baroreceptors in the common carotid artery sense that the pressure has dropped. Person gets up, blood pressure, blood drains from the upper body, creating this blood pressure drop, a homeostatic imbalance that's sensed by a baroreceptor in the common carotid artery above the heart that sends a signal to the integrating center, and I think it's in the medulla oblongata in the brainstem, if I remember right, to the cardiac center in the brainstem, telling it to speed up the heart rate, speed up contractions, to bring the blood pressure up. One other thing that happens here is that the blood vessels constrict in the lower body to bring the blood pressure up. And the restoring blood pressure. So the receptor, the integrating center, and the effector. Stimulus is the change in blood pressure, bringing it back to normal. There are two main control centers or integrating centers. The one that we think of most often is the nervous system. It regulates systems and brings them back into balance. So we have two systems, two control centers, two integrating centers, the nervous system and the endocrine system, which stimulates changes to bring the internal environment back to within the narrow limits of homeostasis. Nervous system acts by nerve impulses via action potentials, which we'll talk about here in a few weeks, but works by nerve signals that cause rapid changes. Most often these changes are short changes where they're quick changes that occur fast and turn off fast as soon as the stimulus is removed. The endocrine system, on the other hand, works by hormones that are secreted from glands into the blood. It acts more slowly, but stays on longer. So these are our two control or integrating centers, that they can work together or independently. So in contrast to a negative feedback loop that pushes things back into the limits that we have, we also have cycles, self-amplifying cycles, where the change causes a greater change, pushing things more out of homeostasis. Bear with me just for a second. So that's the way we've been protecting the bamboo plant, and it actually is the avocado tree. That's how it's actually looking a lot better than it has. I'm sorry, my roommate, who's my mom, just barely walked in the door and she's been gone a week. And we have an avocado plant that we started from a seed. And during our torrential lots of water last week, the plant, whose name is Philip Robert, whom my mother has nicknamed Frobert, did not handle the tropical storm very well last week. So Frobert was outside and now he's inside in the dog pen so that my cats don't attack it. And I was just explaining to her that that's why that Frobert is now in the dog pen. I'll show you really quick. You see the top of Frobert in the little window? So that's Frobert. And now that he's brought back in the house, he's doing a lot better. And so thankfully I was able to save him and he didn't die while my mother was gone. But back to this. So positive feedback loop, self-amplifying cycles, where change results in a greater change in the same direction, pushing things more out of homeostasis. So the most common example and the easiest example to understand is during childbirth. The head of the fetus pushes against the cervix. Baroreceptors in the cervix sense the pressure change and send nerve impulses to the brain, specifically the pituitary gland, to secrete a hormone called oxytocin. So this is the endocrine system secreting oxytocin, which stimulates uterine contractions, pushing the fetus more into the cervix, causing more pressure, more stimulation of baroreceptors, more release of oxytocin, more push of the fetus against the cervix. The cycle keeps occurring until the pressure till the baby is out and there's no more pressure against the cervix. So a positive feedback loop keeps the cycle on the change moving far and farther away from the normal limits until this original stimulus that caused the change the baby's had here is no longer pushing against the cervix and the baby comes out. Any questions about this? Do you see the components of the feedback loop here?
Yes.
So, Brittany, where are they?
As like the components of what the feedback loop is.
Yeah, where do you see the components?
It's the ones that are numbered 1, 2, 3, and 4.
Okay, and what specifically are they? I can tell you have a baby there, but what specifically? What's the receptor?
The receptor is the number 1.
Number one, so the pressure being sensed by this bar receptors within the cervix. What about number 2? Or number, it actually would be number 3, approximately. Number 2, 3.
That's the hold on one second. It's when it's not the effector. Effector is number 4.
It's the integrating or the control center.
That's what it is. I'm sorry. I was looking at my notes.
You know what? I can tell you have a busy household, but I can hear the baby. What's number 4?
That's the effector.
So that's the effector where the uterine contractions continue until the stimulus of the fetus's head is finally not there. Till it's once the fetus is actually removed and the pressure is released off the cervix, the loop stops. But it keeps going until the original stimulus that caused the loop is no longer present.
So in like whenever this is occurring, then really the receptor and the effector is that process is the contractions, and the body keeps going through the contractions until the baby is released.
Right.
Is that correct?
Right. So the contractions are really the response to the change that's occurred, and it just keeps, like Brittany said, it keeps occurring until the pressure is no longer there.
Oh, I know we have to give examples. Would another example be like, say you fell and scraped yourself and you're bleeding? So it's like constantly going through that cycle until you stop bleeding, until that scab like forms? Or like
You know
what
what, Caitlin, you're jumping ahead, but you're right.
Okay.
You're right. So that's the next slide. As Caitlin already jumped into it, that's the next slide.
Sorry, I didn't even look
No,
ahead. I was
you're good.
thinking.
Good job. So a break or tear in the blood vessel wall. Like Caitlin was saying, we get a tear in the blood vessel wall, it starts to bleed. The pressure, or actually it's the fluid moving through the wall there, causes platelets to be activated that become sticky and simultaneously release chemicals. When the platelets become sticky, they start sticking to the broken blood vessel wall. Platelets, when those chemicals that they're also releasing at the same time that they're becoming sticky, activate even more platelets to adhere to the wall and to release more chemicals. And the cycle only ends when there's no more blood flowing through that blood vessel wall. So the feedback cycle loop is initiated by the flow through this wall. And actually can occur with in another pathway, but right now let's just focus on this one, and next semester you'll talk about how it occurs through another pathway. But through this pathway alone, the stimulus that starts it is this flow through the blood vessel wall. Once the flow stops, this cycle stops, and we don't get more platelets becoming activated. Caitlin, do you see how you kind of described this process already?
Yes.
Components of the feedback loop. There's sensors within the vessel wall, receptors within the vessel wall that recognize that the wall's been torn and that there's blood flowing through it. The effector, or excuse me, the control center platelets, then becoming sticky and releasing chemicals as your effector, which then activate more platelets. And now, elaborating a little bit more on Caitlin's question here. Which of the following is an example of a negative feedback system?
I mean, correct me if I'm wrong, but I'm just taking a full-on guess. Is it D? It probably ain't. I'm just forget what I said.
B,
Is it what, Brittany?
B. A decrease in blood pressure.
No. It's a decrease in blood pressure and heart function during severe. The decrease in blood pressure, an increase in blood pressure. Wait, I'm sorry, bear with me here. Decrease in blood pressure and heart function during severe blood loss. No, your heart function is actually going to go up with blood loss. If you've ever heard of someone who goes into, for example, they start to hemorrhage. I'm a big fan of NCIS and sometimes some rather violent books. And what they say is that all of a sudden their pulse becomes very rapid and their skin becomes really pale. And they start to sweat.
Yeah, that's understandable because of blood loss. You faint, after so
Right.
much.
Right.
Well, then negative feedback is whenever the body. I know.
Go ahead, Brittany. Keep going.
Is whenever the body is like, I don't know how to explain it. It goes something more drastic happens, may I say, because the body can't maintain homeostasis, may I say. So like an example of a negative feedback would be like heat exhaustion, right? And then they pass out.
Or yes.
Versus
Yes.
positive feedback would be like heat exhaustion and then the body figures a way to bring him back to homeostasis.
Right, that would be negative.
Okay.
So
So would it be D then?
would it be D?
Because the rash begins to spread.
And then, but then it just itches more. It makes you want to scratch it, right?
Right.
So is that a positive feedback loop? Or is it negative?
I would feel that's negative.
If it itches even more, is that positive or negative? You scratch the rash spreads and it itches even more.
I would say that wouldn't that be positive? Because
It's positive.
it
You're right.
moves the change further and further away from what originally caused the change into
Right.
homeostasis.
Right. So the answer here is E. None of these are examples of negative feedback.
So I guess to better understand, negative is something occurring, like your body temperature, but it's continuously being knocked out, as opposed to positive is it moves the change further and further from what originally caused it until it's completely done, and then that loop is done.
Exactly. Exactly.
I don't know a better way to explain it for like other people to kind of understand, like I'm grasping it, but I think that's the best way to, like,
I think-
positive, it eventually fades away. Negative, it's just continuous.
I think that's a pretty good explanation.
Thank you for that.
Oh, you're welcome. Listen, I'm learning like everybody else. So
Well, hey, you know what? Discussions are really good. Discussions are good. And I mean, especially when we're in class like this, where we're all coming from separate homes and separate environments, discussions are really good. Midway through a 5-mile workout, a runner begins to sweat profusely. The sweat glands producing the sweat would be considered which part of a feedback loop?
Wouldn't it be the effector?
Say it one more time.
I said, wouldn't it be the effector?
I think you're right. It's the effector. And you guys, I'm going to get my dog out. Give me 1 second. My mom came home with the dog. I'm going to get her out because she's going to make me crazy. Give me 1 second. So if you want to see my dog, there's my dog. My mom just got back from Virginia where we ended up putting down one of our dogs. And from what I've understood, this little dog, the one that we have left, has become very clingy. And so the fact that my mother walked out the door and left her here made her really unhappy all of a sudden. Well, Paisley, stay here.
She's really cute. Oh,
She is. She says, I'm very friendly and I'm very full of myself. Oh.
Poodles
Yeah.
are really smart too.
They are, and she's almost too smart for her own good. Stay.
So she's very cute.
She's really sweet. We have a field across the street where students play lacrosse. And when we take her outside to go to the bathroom, if we don't watch her, the next thing you know, she's over there making friends with all the girls on the lacrosse team.
Oh,
Yeah, so I'm almost too smart for my own good. So Homeostasis is constantly being disrupted. We have physical insults. We have changes within the internal environment, physiological stress. A mild and temporary disruption results in balance being quickly restored. Intense or prolonged disruption results from poisoning or severe infections. So homeostatic imbalances are when the normal equilibrium of body processes are being disrupted. A moderate imbalance is an abnormality of structure and function, a disorder. If you think about the fact, remember that complementarity? Paisley, stop, baby, stop. Okay, stay. So if you think about that complementarity, you change the structure, you change the function. A disorder, a change in the structure. Disease. A change, an abnormality that's specific for an illness with recognizable signs and symptoms. Local disease or change in the structure and function that affects one body or a limited region of the body. So an abnormality of structure and function that affects one part of the body or a limited region of the body. Systemic disease, an abnormality of structure and function that then affects either the entire body or several parts. Symptoms are subjective changes such as headache or nausea that are not measurable or observable by a clinician or other individual. Signs are objective changes such as a fever or swelling in which a clinician can observe and measure. Or, let me say it this way, changes such as a fever or swelling that can be observed or measured by a clinician. A severe imbalance is death. Is this a symptom or a sign? Fatigue.
Symptom.
It's a symptom. Why is it a symptom, Brittany?
I'm not quite sure.
Can you observe someone else's fatigue? You might be able to observe it, but can you measure it?
No.
That's the reason. What about a headache?
Symptom.
It's a symptom. Joint pain,
Symptom.
Symptom.
it's a symptom. A bullseye rash,
Sign.
Fine.
That's a sign.
it's a sign. A blood test that's positive for Borrelia burgdorferi, whatever that is.
Sign.
Fine.
A tick bite,
Fine.
and Bell's palsy.
Fine.
Suri goes to her family doctor and tells her that she has a headache and she feels nauseated. The doctor checks Suri's temperature and finds that she has a fever. In the above situation, Suri's headache is a symptom of an illness, while the fever is a sign of illness. True or false?
True.
True.
Okay, last part of this chapter, gradients. Gradients are difference in chemical concentration, charge, temperature, or pressure between 2 points. So there's a difference in between 2 points with regards to chemical, charge, temperature, or pressure. Matter and energy, all things tend to flow downhill. If everything, one overall right theme to physiology is everything moves from high to a low. Everything always goes down a gradient from a high to a low. Unless you physically force it to not move that direction. So blood flows from a place of higher pressure to a place of lower pressure. Heat moves from a higher temperature to a lower temperature. If we put some dye in some water, the dye is going to move from where it's most concentrated to where it's less concentrated until there's no longer a gradient across the volume of water. Movement in the opposite direction is going up the gradient and requires some form of energy, metabolic energy, to make that occur. So if we allow it, everything will move from a high to a low. And it's spontaneous. It's always going to occur that way unless we put in some energy and force it to move the other direction or to not move. A couple different types of gradients. Chemicals flow down concentration gradients. Charged particles flow down electrical gradients. We also have what's called an electrochemical gradient, which is charged chemicals. Or a mix of a concentration and an electrical gradient, a charged chemical gradient. Heat flows down thermal gradients. So spontaneously, all things are going to move from a high to a low unless we physically put in some energy to stop it or push it in the opposite direction. Any questions about this? This is chapter 1. Okay, so this is the end of chapter 1. Oh, that wasn't good. When does our class end? Is it 2:10 or 2:20? I'm sorry, is it 12? Yeah, is it, excuse me, not 2:10. Is it 1:10 or 1:20?
I think it's 1:45 is the end.
Oh, really?
Yeah, I think it's
1:45?
1:45.
So
Yeah, it's
did I go,
1:45.
so I went significantly over?
That's okay.
Really? I'm so sorry. Okay, I will see you guys on Thursday at the same place. So we'll start chapter 2. And I apologize. So sorry. Feel
Don't
free
worry
to
at
tell
all.
me, feel free to tell me it's now 1:45, Sister Gessel. Stop talking. Okay? Stop talking and be done. All
That
right.
was the last slide anyway, so
I'm so sorry. You guys have a wonderful day, okay?
thank you.
You too.
You too. Bye.
Mom, eventually I'll get all my times right. I tried to tell him. I sent you the message at the same time I told him.
Was it a text?
Yes. You go tell her you're not ready. Say this coveted potato came and got me, but it doesn't have the same effect.